Picture this. You're holding a grain of sand, and someone tells you that this tiny speck is rarer than finding a needle in a haystack the size of our entire galaxy. Sounds impossible, right? Well, welcome to the universe's most exclusive club. Objects so incredibly rare that some exist in numbers you can count on your fingers, while others might not exist at all in our observable cosmos. Today, we're going on a journey to discover these cosmic unicorns, the rarest phenomena that make winning the lottery look like a daily occurrence. If you're curious about these mysteries, make sure to subscribe to this channel and give a thumbs up. I am just starting my journey on YouTube, and your support means a lot to me. When we talk about rarity in space, we're not just discussing something uncommon. We're exploring objects that challenge our understanding of physics itself. These cosmic treasures tell us stories about the universe's most extreme conditions, its violent past, and perhaps even its ultimate destiny. Each discovery reshapes how we perceive reality and our place within this magnificent cosmic dance. Our journey begins with perhaps the most mysterious category of rare objects, those born from the universe's infancy. During the first fraction of a second after the Big Bang, conditions were so intense that matter behaved in ways we're only beginning to understand. The temperature exceeded trillions of degrees, and the density was incomprehensible. In this cosmic furnace, some regions became slightly denser than others, and as the universe expanded and cooled, these density fluctuations had profound consequences. But here's where things get truly fascinating. Some scientists believe that during this primordial epoch, the universe created objects called primordial black holes. Unlike the black holes we're familiar with today, which form when massive stars collapse, these ancient giants supposedly formed directly from the intense density fluctuations of the early universe. If they exist, primordial black holes could range from microscopic sizes to masses larger than our Sun, and they would be among the oldest objects in existence. The James Webb Space Telescope, launched in 2021, has been revolutionizing our understanding of these early cosmic epochs. Every image it captures is like looking through a time machine, showing us how the universe appeared when it was just a cosmic infant. The telescope's incredible sensitivity allows us to peer deeper into space, and therefore further back in time than ever before. What makes primordial black holes so incredibly rare isn't just their hypothetical nature, but the precise conditions required for their formation. The density fluctuations in the early universe had to be just right, not too small to collapse under their own gravity, but not so large that they would have disrupted the formation of the cosmic structure we see today. It's like trying to hit a target the size of a pinhead while blindfolded and spinning. Recent discoveries from the Laser Interferometer Gravitational Wave Observatory, or LIGO, have detected gravitational waves from merging black holes with unexpected masses. Some of these detections have led scientists to wonder if we might actually be observing the gravitational signatures of primordial black holes colliding. If confirmed, this would represent direct evidence of objects that have existed since the universe was less than 1 second old. But primordial black holes aren't the only relics from the universe's childhood that might still be hiding in plain sight. Magnetic monopoles, hypothetical particles that would have only one magnetic pole instead of the usual two, could have formed during the universe's first moments. While we've never detected one, their existence would solve several puzzles in particle physics and cosmology. The search for magnetic monopoles represents one of the most challenging quests in modern physics. Unlike regular magnets, which always have both north and south poles, a magnetic monopole would be like having just the north pole of a magnet floating freely in space. The laws of physics as we understand them suggest these objects should exist, yet despite decades of searching with increasingly sophisticated detectors, we haven't found a single one. The rarity of magnetic monopoles highlights something profound about our universe. Sometimes the most theoretically important objects are also the most elusive. This paradox leads us to our next category of cosmic rarities, objects so massive and energetic that they exist at the very limits of what physics allows. Enter magnetars, neutron stars with magnetic fields so powerful they make the strongest magnets on Earth look like refrigerator decorations. To understand just how rare magnetars are, consider this. Out of the roughly 2,000 neutron stars we've discovered, fewer than 30 are confirmed magnetars. That's like finding a specific type of flower in a field where only one in every 67 plants is the variety you're seeking. But here's what makes magnetars truly extraordinary. Their magnetic fields are a quadrillion times stronger than Earth's. If a magnetar existed at half the distance from Earth to the Moon, its magnetic field would erase every credit card on our planet and disrupt the electrical activity in every living brain. The field is so intense that it warps the very atoms around the star, stretching them into thin, needle-like shapes. The formation of a magnetar requires a perfect storm of cosmic circumstances. When a star at least 10 to 25 times more massive than our Sun reaches the end of its life, it undergoes a catastrophic collapse. In less than a second, the star's core, originally the size of Earth, compresses to a sphere only 12 miles across. This compression is so extreme that a teaspoon of neutron star material would weigh about 6 billion tons. For a neutron star to become a magnetar, the collapse must occur in just the right way to amplify the original star's magnetic field by factors we can barely comprehend. The exact mechanism remains one of astrophysics' greatest mysteries. Some theories suggest that the intense turbulence during the collapse creates a dynamo effect, similar to how Earth generates its magnetic field, but amplified beyond imagination. The Chandra X-ray Observatory and the Swift Gamma-ray Burst mission have been instrumental in identifying and studying these cosmic lighthouses. When magnetars experience what astronomers call starquakes, sudden rearrangements of their crystalline crusts, they release more energy in 1/10 of a second than our Sun produces in 100,000 years. These outbursts can be detected from thousands of light years away. One of the most famous magnetars, designated SGR 1806-20, sits about 50,000 light-years from Earth in the constellation Sagittarius. On December 27, 2004, this magnetar experienced the most powerful explosion ever recorded in our galaxy. The burst of gamma rays was so intense that it temporarily blinded satellites, disrupted radio communications on Earth, and caused our planet's upper atmosphere to expand measurably. But even magnetars pale in comparison to our next cosmic rarity, quark stars. These hypothetical objects represent matter in a state so exotic that we're not even certain they can exist. If they do, quark stars would be composed of free quarks, the fundamental particles that normally exist only inside protons and neutrons. Under the crushing pressure of a collapsing neutron star, some scientists theorize that even neutrons and protons break apart, creating a soup of individual quarks. The conditions required to create a quark star are mind-boggling. The pressure must be high enough to overcome the strong nuclear force that normally binds quarks together, yet not so high that the object collapses into a black hole. This narrow window of possibility makes quark stars potentially rarer than any other type of stellar remnant. Recent observations from the Neutron Star Interior Composition Explorer, or NICER, aboard the International Space Station, have provided tantalizing hints about the interior structure of neutron stars. Some measurements suggest that the cores of the most massive neutron stars might indeed contain free quarks, supporting the possibility that quark stars, or at least neutron stars with quark matter cores, actually exist. The search for quark stars exemplifies how the rarest objects in the universe often exist at the boundaries of our knowledge. These aren't just astronomical curiosities, they're natural laboratories where the fundamental forces of nature are pushed to their absolute limits. By studying them, we're essentially conducting experiments that we could never perform on Earth. This brings us to perhaps the most philosophically challenging category of rare cosmic objects, those that exist in states of matter we've never encountered. Scientists have identified several possible exotic states that might exist only in the universe's most extreme environments. Strange matter, composed of strange quarks, represents one such possibility. According to some theories, strange matter might be more stable than normal matter under certain conditions. If this is true, contact between strange matter and normal matter would convert regular atoms into strange matter, potentially transforming entire planets or stars in a cascading reaction. The concept of strange matter takes us into territory where science fiction and science fact begin to blur. Imagine a substance so fundamentally different from everything we know that a single drop could theoretically convert all matter on Earth into an alien form of material. This isn't the plot of a blockbuster movie. It's a legitimate scientific hypothesis that emerges from our understanding of quantum chromodynamics, the theory describing how quarks interact. Strange quarks are one of the 6 known types of quarks, but they're incredibly unstable under normal conditions. They decay almost instantly into the lighter up and down quarks that make up protons and neutrons. However, theoretical physicists have calculated that under the extreme pressures found in neutron star cores, strange quarks might become stable, even more stable than normal matter. If strange matter truly represents the most stable configuration of matter in the universe, then every atom we see around us, including the atoms in our own bodies, exists in a metastable state, like a ball balanced precariously on the edge of a cliff. The implications are staggering. Some scientists have speculated that strange matter objects, called strangelets, might already exist somewhere in the cosmos, wandering through space as the ultimate cosmic nomads. The relativistic heavy ion collider at Brookhaven National Laboratory has conducted experiments to search for strangelets, accelerating gold nuclei to nearly the speed of light and smashing them together to recreate conditions similar to those inside neutron stars. Despite years of searching, researchers haven't found definitive evidence for stable strange matter, but the quest continues with ever more sophisticated detection methods. This search connects us to one of the most profound questions in physics. What is the true ground state of matter? Everything we see, from the smallest bacteria to the largest galaxies, might exist only because the universe hasn't yet discovered a more stable way to organize its fundamental building blocks. It's both humbling and awe-inspiring to consider that we might be living in a universe that's essentially in a temporary state of existence. Moving from the realm of exotic matter to the domain of spacetime itself, we encounter objects that challenge our understanding of reality's very fabric. Cosmic strings, if they exist, would be one-dimensional defects in spacetime, thinner than a proton but potentially stretching across the entire observable universe. Think of them as the universe's equivalent of cracks in a sheet of ice, formed as the cosmos cooled and underwent phase transitions in its earliest moments. The theoretical framework for cosmic strings emerges from string theory and grand unified theories of physics. During the universe's infancy, as it cooled from unimaginable temperatures, different regions might have settled into slightly different vacuum states. The boundaries between these regions would form cosmic strings, topological defects that carry enormous energy and could have profound gravitational effects. A cosmic string with the mass of a mountain compressed into a one-dimensional line would create gravitational effects detectable across astronomical distances. These objects would bend spacetime so dramatically that light passing on opposite sides of a cosmic string would arrive at Earth at slightly different times, creating a distinctive signature that astronomers call gravitational lensing. The Planck satellite, which operated from 2009 to 2013, searched for evidence of cosmic strings by looking for specific patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. While no definitive evidence has been found, the absence of detection actually tells us something important about the early universe's history and the energy scales at which fundamental physics operates. But perhaps the most mind-bending aspect of cosmic strings isn't their incredible length or mass. It's their potential ability to generate closed time-like curves. Theoretical calculations suggest that 2 cosmic strings passing by each other at high speed could create conditions where spacetime becomes so warped that time travel into the past becomes possible. This brings us face to face with causality paradoxes and questions about the fundamental nature of time itself. The search for cosmic strings represents humanity's attempt to understand events that occurred when the universe was less than a billionth of a billionth of a billionth of a second old. We're essentially cosmic archaeologists, using the most advanced telescopes and detectors to search for fossils from an era when the laws of physics themselves might have been different. This brings us to another category of extremely rare objects: primordial gravitational waves. Unlike the gravitational waves detected by LIGO and Virgo, which come from merging black holes and neutron stars, primordial gravitational waves would be direct messengers from the Big Bang itself. These ripples in spacetime would carry information about the universe when it was younger than the time it takes light to travel across a single atom. The detection of primordial gravitational waves would open an entirely new window into the cosmos, allowing us to probe conditions that existed before the universe became transparent to light. Currently, our earliest direct observations of the universe come from the cosmic microwave background radiation, which originated when the universe was about 380,000 years old. Primordial gravitational waves could potentially tell us about events that happened in the first tiny fraction of the first second. Several next-generation gravitational wave detectors are being planned or constructed to search for these cosmic whispers. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will consist of 3 spacecraft separated by millions of kilometers, creating a gravitational wave detector larger than Earth itself. If primordial gravitational waves exist at detectable levels, LISA might finally capture them. The rarity of primordial gravitational waves isn't just about their age, it's about their incredible weakness. These waves would be so faint that detecting them would be like hearing a whisper from across a crowded stadium during a rock concert. The fact that we're even attempting such measurements speaks to both human ingenuity and our deep desire to understand our cosmic origins. The search for primordial gravitational waves connects us to an even more mysterious aspect of cosmic rarity: objects and phenomena that might exist but remain completely invisible to conventional astronomy. We live in a universe where roughly 85% of all matter is dark matter, a substance that doesn't emit, absorb, or reflect light, yet whose gravitational effects shape the very structure of the cosmos. But within this already mysterious dark sector, there might exist objects so rare and exotic that they challenge our imagination. Dark matter stars, for instance, represent a hypothetical class of stellar objects powered not by nuclear fusion like our Sun, but by the annihilation of dark matter particles. If they exist, these ghostly giants could be among the first stars that ever formed in the universe, shining with a cold, otherworldly light invisible to our eyes, but potentially detectable through their gravitational effects. The concept of dark matter stars emerged from computer simulations of the early universe conducted by researchers using some of the world's most powerful supercomputers. These models suggest that in the universe's infancy, when dark matter was much denser than it is today, certain regions might have accumulated enough dark matter to form self-gravitating objects. Unlike normal stars, which burn through their nuclear fuel and eventually die, dark matter stars could theoretically persist for billions of years, fed by the continuous annihilation of dark matter particles in their cores. The European Space Agency's Euclid mission, launched in July 2023, is mapping the distribution of dark matter throughout the universe with unprecedented precision. While Euclid wasn't specifically designed to search for dark matter stars, its detailed surveys might reveal gravitational anomalies that could point toward these invisible giants lurking in the cosmic shadows. But dark matter stars aren't the only exotic objects that might populate the dark sector. Some theoretical physicists have proposed the existence of Axion stars, clumps of hypothetical particles called axions that could form gravitationally bound objects roughly the size of Earth, but with masses comparable to small moons. Axions were originally proposed to solve certain problems in particle physics, but if they exist, they could make up a significant fraction of dark matter. The remarkable thing about Axion stars is that they would be almost completely invisible to normal matter, passing through planets and stars like cosmic ghosts. However, in the presence of strong magnetic fields, such as those found around neutron stars or in laboratory experiments, axions might convert into photons, making them potentially detectable. The Axion Dark Matter Experiment, or ADMX, at the University of Washington, has been searching for these conversions for over 2 decades. This brings us to perhaps one of the most unsettling categories of rare cosmic objects, those that could theoretically destroy everything we know and love. Vacuum decay bubbles represent the ultimate cosmic nightmare, expanding spheres of space where the laws of physics themselves have changed, moving outward at the speed of light and converting everything they touch into a fundamentally different state of reality. The possibility of vacuum decay emerges from our understanding of quantum field theory and the Higgs field that permeates all of space. Just as water can exist as liquid, ice, or steam depending on temperature and pressure, the quantum vacuum might exist in different states. If our current vacuum state is only metastable, meaning it's not the absolute lowest energy configuration possible, then quantum fluctuations could occasionally trigger transitions to a lower energy state. The discovery of the Higgs boson at CERN's Large Hadron Collider in 2012 allowed physicists to calculate more precisely whether our universe exists in a stable or metastable vacuum state. The results are somewhat unsettling. Based on the measured properties of the Higgs boson and the top quark, our universe appears to be in a metastable state, balanced on the edge between stability and decay. If a vacuum decay bubble ever formed, it would expand at light speed, and nothing could stop or outrun it. The physics inside the bubble would be completely different from our own. Atoms might not be able to exist, the fundamental forces could have different strengths, and the very concept of matter as we know it might become meaningless. It would be the ultimate cosmic reset button, erasing not just life but the very possibility of complexity and structure. The good news is that such an event is extraordinarily unlikely on timescales relevant to human civilization. The probability of spontaneous vacuum decay is so small that it would typically take far longer than the current age of the universe for such an event to occur naturally. However, extremely high-energy processes, perhaps involving physics beyond our current understanding, might theoretically trigger such transitions. This existential cosmic threat highlights something profound about the rarity we've been exploring. Some of the universe's rarest objects and phenomena represent not just scientific curiosities, but fundamental questions about the nature of existence itself. Each discovery forces us to confront how little we truly know about the cosmos we inhabit. Moving from cosmic nightmares to cosmic mysteries, let's explore another category of incredibly rare objects: rogue planets. These are worlds that have been ejected from their parent star systems and now drift alone through interstellar space, unbound by any star's gravity. Recent estimates suggest there might be billions of these cosmic orphans wandering through our galaxy, but detecting them is extraordinarily challenging because they emit no light of their own. The formation of rogue planets represents one of the most violent processes in planetary system evolution. Computer simulations show that during the early, chaotic phases of planetary system formation, gravitational interactions between forming planets can become so intense that some worlds are literally flung out of their birth systems at speeds exceeding the escape velocity. These cosmic refugees then begin billion-year journeys through the cold, dark void between stars. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the first comprehensive survey for rogue planets using a technique called gravitational microlensing. When a rogue planet passes in front of a distant star from our perspective, its gravity acts like a lens, briefly brightening the background star in a characteristic way. These events are incredibly rare. A given star might be microlensed by a rogue planet only once in several million years. The discovery of rogue planets forces us to reconsider what makes a world habitable. Without a star's warmth, these wandering worlds exist in temperatures close to absolute zero. Yet some scientists speculate that large rogue planets with thick atmospheres and substantial internal heat from radioactive decay might maintain liquid oceans beneath frozen surfaces, similar to Jupiter's moon Europa or Saturn's moon Enceladus. The possibility of life on rogue planets opens our minds to just how adaptable and persistent biology might be throughout the cosmos. If microorganisms can survive in the deep ocean trenches of Earth, in boiling hot springs, and even in the vacuum of space, Perhaps they could also find ways to thrive on worlds that have been cast adrift between the stars. These scenarios force us to expand our definition of habitable zones far beyond the traditional concept of planets orbiting safely within a star's warmth. The Kepler Space Telescope, during its operational years from 2009 to 2018, revolutionized our understanding of planetary systems and inadvertently provided insights into how common planetary ejections might be. By observing the orbital dynamics of thousands of planetary systems, astronomers developed computer models showing that for every planet that remains in a stable orbit, one or more might be ejected into interstellar space during the chaotic early stages of system formation. This brings us to another extraordinary class of cosmic wanderers, hypervelocity stars. These are individual stars moving so fast through our galaxy that they're actually in the process of escaping the Milky Way entirely. Traveling at speeds exceeding 500 kilometers per second, fast enough to cross the United States in about 12 seconds, these stellar refugees represent some of the most extreme outcomes of gravitational interactions in the universe. The mechanism behind hypervelocity stars involves some of the most dramatic events in galactic astronomy. Most of these cosmic speedsters are thought to originate from close encounters with Sagittarius A star, the supermassive black hole at our galaxy's center. When a binary star system wanders too close to this 4 million solar mass monster, the intense gravitational forces can tear the pair apart, sending one star plummeting into the black hole while flinging its companion outward at incredible velocity. The first hypervelocity star, designated He 0543-454, was discovered in 2005 by astronomers using the MMT Observatory in Arizona. This particular star is traveling at over 700 kilometers per second, so fast that it will escape our galaxy entirely and spend eternity wandering through the cosmic void between galaxies. Since that initial discovery, astronomers have identified several dozen more of these stellar exiles. The European Space Agency's Gaia mission has been instrumental in identifying hypervelocity stars by precisely measuring the positions and motions of over 1 billion stars in our galaxy. Gaia's unprecedented accuracy allows astronomers to trace stellar motions backward in time, confirming that many hypervelocity stars indeed originate from the galactic center. Some of these stars have been traveling for tens of millions of years, carrying with them any planetary systems that managed to survive the violent ejection process. But hypervelocity stars aren't the only stellar objects that challenge our understanding of normal galactic dynamics. We've also discovered stars moving in completely unexpected directions, suggesting they might be visitors from other galaxies entirely. These intergalactic immigrants could be remnants from small galaxies that the Milky Way has consumed over its long history, or they might be hypervelocity stars ejected from neighboring galaxies like Andromeda. The concept of intergalactic stars leads us to consider the vast spaces between galaxies, regions so empty that a single atom per cubic meter represents a relatively dense environment. Yet even in these cosmic voids, rare and exotic objects might exist. Some theoretical models suggest that primordial black holes, if they exist, could be distributed throughout intergalactic space, invisible gravitational lighthouses marking the universe's earliest epoch. Speaking of black holes, let's explore one of the most puzzling categories in the black hole family tree: intermediate mass black holes. While we've confirmed the existence of stellar mass black holes formed from collapsed stars, and we've observed supermassive black holes millions of times more massive than our Sun at galactic centers, the middle ground remains frustratingly empty. Intermediate mass black holes, with masses between 100 and 100,000 times that of our Sun, are among the most sought-after objects in modern astronomy. The rarity of intermediate mass black holes represents one of astrophysics' greatest mysteries. Computer simulations suggest they should exist. Stellar mass black holes should occasionally merge and grow, while supermassive black holes must have started somewhere. Yet despite decades of searching, we found only a handful of candidates, and even those remain controversial. The Hubble Space Telescope has provided some of the most compelling evidence for intermediate mass black holes by observing the centers of globular clusters, ancient collections of hundreds of thousands of stars that orbit our galaxy like cosmic beehives. In several of these clusters, stars near the center move at speeds that suggest they're orbiting an invisible massive object. However, proving that these objects are actually black holes rather than dense collections of neutron stars or stellar mass black holes remains challenging. The recent detection of gravitational waves has opened new possibilities for finding intermediate mass black holes. When LIGO detected the merger of two black holes with 36 and 29 solar masses respectively, astronomers realized they were observing black holes more massive than any known stellar mass black hole in our galaxy. These detections suggest that intermediate mass black holes might be more common than previously thought, hiding in regions of space where traditional astronomical techniques can't detect them. The search for intermediate mass black holes highlights a fundamental challenge in studying the universe's rarest objects. Absence of evidence isn't evidence of absence. Just because we haven't found something doesn't mean it doesn't exist. It might simply be incredibly difficult to detect with our current technology and observational techniques. This principle applies to many of the rare objects we've discussed. Dark matter stars, Axion clumps, cosmic strings, and primordial black holes might all exist in numbers that make them technically common on cosmic scales, yet remain undetected because they interact so weakly with normal matter or because the signatures they produce are incredibly subtle. The James Webb Space Telescope is already changing this landscape by detecting objects that previous telescopes couldn't see. Its infrared vision allows it to peer through cosmic dust clouds and observe the universe's earliest galaxies, potentially revealing populations of objects that have remained hidden until now. Every new image from Webb contains the possibility of discovering something unprecedented. The transformative power of new observational tools becomes even more apparent when we consider objects so rare that we've detected only one or two examples in the entire observable universe. Thorne-Żytkow objects represent perhaps the most bizarre stellar hybrids imaginable: red supergiant stars with neutron star cores. Picture a star so massive and luminous that it could contain our entire solar system, yet at its heart lies a city-sized sphere of matter so dense that a teaspoon would outweigh Mount Everest. The theoretical foundation for these cosmic chimeras was laid in 1975 by Nobel Prize winner Kip Thorne and astronomer Anna Żytkow. They proposed that in rare circumstances, a neutron star could survive being engulfed by a red supergiant companion, spiraling inward until it replaces the giant star's normal core. The result would be a stellar object unlike anything else in the universe, a star powered not by nuclear fusion, but by the accretion of matter onto an incredibly dense neutron star core. The rarity of Thorne-Żytkow objects stems from the extraordinary sequence of events required for their formation. First, a massive binary star system must evolve in just the right way. One star must explode as a supernova while keeping the neutron star remnant in orbit around its companion. Then, the surviving star must evolve into a red supergiant and expand to enormous size. Finally, the neutron star must spiral inward through the giant's envelope without being destroyed or ejecting too much material to disrupt the process. For decades, these objects remained purely theoretical curiosities. Then, in 2014, astronomers announced the discovery of HV 2112, a red supergiant in the Small Magellanic Cloud with chemical signatures that couldn't be explained by normal stellar evolution. The star showed unusual abundances of lithium, molybdenum, and other elements that matched theoretical predictions for what the interior of a Thorne-Żytkow object should produce. The discovery process itself illustrates how rare object detection often requires combining multiple lines of evidence. Astronomers use spectroscopy to analyze the star's light, revealing chemical fingerprints that told the story of exotic nuclear processes occurring in its core. These weren't the typical fusion reactions that power normal stars, but rather the complex nuclear cascades that would occur when matter falls onto a neutron star surface at thousands of kilometers per second. But even Thorne-Żytkow objects pale in cosmic significance compared to the sources of some of the universe's most spectacular explosions, Kilonovae. These titanic events occur when two neutron stars spiral into each other and merge, creating conditions so extreme that they forge elements that can't be produced anywhere else in the universe. Every atom of gold in your jewelry, every platinum catalyst in modern technology, and most of the silver in photography was born in the heart of a Kilonovae explosion. The 2017 detection of gravitational waves from merging neutron stars, designated GW 170817, marked the beginning of a new era in astronomy. For the first time, scientists detected the same cosmic event using both gravitational waves and traditional electromagnetic observations. The merger, occurring in a galaxy 130 million light-years away, was observed by over 70 telescopes worldwide, making it one of the most thoroughly studied events in astronomical history. The gravitational wave signal told the story of two neutron stars, each containing more mass than our Sun compressed into spheres only 12 miles across, orbiting each other 11 times per second before their final collision. The electromagnetic observations revealed the spectacular aftermath, a fireball expanding at one-third the speed of light, glowing with the combined luminosity of 100 million suns, and synthesizing more than 10 Earth masses worth of gold and platinum in just a few seconds. The rarity of observable Kilonovae events reflects both the uncommon nature of neutron star binaries and the precise conditions required for detection. Neutron star mergers might occur once every 10,000 to 100,000 years in a typical galaxy, but most of these events happen so far away that their signals are too weak to detect with current instruments. The fact that we detected GW 170817 at all represents an extraordinary stroke of astronomical fortune. The scientific impact of this detection extends far beyond astrophysics. For the first time, astronomers could directly observe the cosmic factories where nature forges the heaviest elements. Computer simulations of the merger show matter being heated to temperatures of billions of degrees, while experiencing pressures exceeding those in atomic nuclei. Under these conditions, rapid neutron capture processes create unstable isotopes that decay into the stable heavy elements essential for rocky planets and technological civilizations. This connection between cosmic explosions and terrestrial existence exemplifies one of the most profound themes in modern astronomy. We are intimately connected to the rarest and most violent events in the universe. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all forged in stellar cores and dispersed by supernovae. But the gold in our electronics and the silver in our mirrors required even rarer conditions, the collision of two of the densest objects in existence. The study of Kilonovae has also provided crucial insights into one of cosmology's biggest mysteries, the rate at which the universe is expanding. By combining gravitational wave measurements of distance with optical observations of recession velocity, astronomers can calculate the Hubble constant, a fundamental parameter describing cosmic expansion, using a completely independent method from traditional techniques. This measurement technique, dubbed standard sirens in analogy to the standard candles used in traditional cosmology, has revealed a puzzling discrepancy. The expansion rate measured using Kilonovae observations doesn't quite match the rate calculated from cosmic microwave background observations. This tension might indicate new physics beyond our current understanding of the universe. Moving from the realm of stellar explosions to even more exotic scenarios, let's explore gamma-ray bursts, the most powerful electromagnetic explosions in the universe since the Big Bang. These cosmic lighthouses can outshine entire galaxies for seconds or minutes, releasing more energy in that brief time than our Sun will produce over its entire 10 billion-year lifetime. The discovery of gamma-ray bursts represents one of the most serendipitous findings in the history of astronomy. In the 1960s, the United States launched the Vela satellites to monitor for nuclear weapons tests banned by international treaty. Instead of detecting terrestrial bomb tests, these spacecraft discovered mysterious bursts of gamma rays coming from random directions in space. For decades, the origin of these bursts remained one of astronomy's greatest mysteries. The mystery of gamma-ray bursts deepened throughout the 1970s and 80s as more sophisticated detectors revealed their incredible diversity. Some bursts lasted only milliseconds, while others persisted for several minutes. Some repeated unpredictably, while others appeared to be one-time events. The energy requirements seemed impossible to explain. If these bursts were truly at cosmological distances, they would represent the most powerful explosions in the known universe. The breakthrough came in 1997 when the Italian-Dutch satellite Bepo-SEX detected the afterglow of a gamma-ray burst in visible light. For the first time, astronomers could pinpoint the exact location of a burst and study its host galaxy. The results were staggering. The burst originated from a galaxy billions of light-years away, confirming that these events were indeed among the most energetic phenomena in the cosmos. Today, we understand that gamma-ray bursts come in two main varieties, each representing a different type of cosmic catastrophe. Short-duration bursts, lasting less than 2 seconds, appear to result from the merger of neutron stars or neutron-star black hole pairs, events similar to the Kilonovae we discussed earlier. Long-duration bursts, which can persist for several minutes, are thought to mark the deaths of the most massive stars in the universe as they collapse into black holes. The most extreme gamma-ray burst ever detected, designated GRB 210425A, was discovered in April 2021 by multiple space-based observatories. This cosmic monster released more energy in just 10 seconds than our Sun will produce in its entire lifetime. The burst was so bright that it would have been visible to the naked eye despite occurring over 4 billion light-years away, a distance so vast that the light we detected began its journey before Earth even formed. What makes gamma-ray bursts particularly rare isn't just their incredible power, but the precise geometric conditions required for detection. Current models suggest that these explosions emit most of their energy in narrow jets, like cosmic lighthouses with beams only a few degrees wide. This means that for every gamma-ray burst we detect pointing toward Earth, there might be hundreds of similar events occurring throughout the universe that we never see because their jets point in other directions. The study of gamma-ray bursts has opened windows into some of the most extreme physics in the universe. The jets responsible for these explosions travel at speeds exceeding 99% the speed of light, creating conditions where Einstein's special theory of relativity becomes crucial for understanding the observed phenomena. Time dilation effects mean that processes occurring over seconds in the burst's reference frame can appear to last much longer when observed from Earth. But perhaps even more mysterious than gamma-ray bursts are fast radio bursts, intense flashes of radio waves that last only milliseconds but can be detected from billions of light-years away. The first fast radio burst was discovered in 2007 by astronomer Duncan Lorimer while analyzing archived data from the Parkes Radio Telescope in Australia. The burst, now known as the Lorimer burst, appeared as a single spike of radio emission lasting just 5 milliseconds. What made this detection so puzzling was the burst's dispersion, the way radio waves of different frequencies arrived at slightly different times. This effect occurs when radio waves travel through ionized gas in space, and the amount of dispersion indicated that the burst had traveled through far more material than exists in our galaxy. The inescapable conclusion was that this brief radio flash had originated from an extragalactic source, requiring enormous energies to be detectable across such vast distances. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, has revolutionized fast radio burst astronomy since beginning operations in 2018. This innovative telescope uses 4 massive cylindrical reflectors to monitor the entire northern sky simultaneously, detecting dozens of fast radio bursts each month. The flood of new detections has revealed that these mysterious signals are far more common than initially thought. Most fast radio bursts appear to be one-time events, leading to intense speculation about their origins. Proposed explanations include everything from colliding neutron stars to exotic matter interactions, from alien transmissions to the evaporation of primordial black holes. The brief duration and enormous distances involved make it incredibly difficult to study these events in detail or test theoretical models against observations. However, in April 2020, astronomers made a breakthrough discovery that provided the first major clue about fast radio burst origins. A radio burst was detected coming from within our own galaxy, originating from a known magnetar designated SGR 1935 plus 2154. This burst was far less energetic than the extragalactic fast radio bursts, but it proved that at least some of these mysterious signals can be produced by highly magnetized neutron stars. The galactic fast radio burst detection solved one mystery while deepening another. If magnetars can produce fast radio bursts, why are the extragalactic versions so much more powerful? Some astronomers speculate that the most extreme fast radio bursts might come from a special class of magnetars with magnetic fields even stronger than previously thought possible, or from magnetars undergoing particularly violent eruptions. The search for fast radio burst sources has also led to an unexpected discovery about the cosmic web, the vast network of gas filaments that connects galaxies throughout the universe. The dispersion measurements of extragalactic fast radio bursts provide a way to probe this otherwise invisible material, allowing astronomers to map the distribution of ionized gas between galaxies with unprecedented precision. This brings us to perhaps the most exotic theoretical objects we'll explore: white holes and wormholes. While black holes represent regions where matter and energy can enter but never escape, white holes would be their theoretical opposites, regions that can only emit matter and energy, never absorbing anything. If they exist, white holes would appear as brilliant sources of radiation, continuously spewing matter and energy into space without any apparent fuel source. The mathematical description of white holes emerges naturally from Einstein's general theory of relativity. The same equations that predict black holes also allow for their time-reversed counterparts. However, while black holes are stable objects that can persist indefinitely, white holes would be fundamentally unstable. Any matter approaching a white hole would be repelled by the intense radiation pressure, but quantum effects and realistic astrophysical environments would quickly destroy these exotic objects. Some cosmologists have speculated that the Big Bang itself might have been a white hole, a cosmic fountain from which all matter and energy in our universe emerged. This idea attempts to address one of the deepest questions in cosmology: what came before the Big Bang? If our universe's birth was actually a white hole event, it might be connected through spacetime to another universe or region of reality entirely. Wormholes represent another category of exotic spacetime structures that emerge from Einstein's equations. These hypothetical tunnels through spacetime would connect distant regions of the universe, potentially allowing for faster-than-light travel or even time travel. Science fiction has embraced wormholes as cosmic highways, but the physics of these objects presents formidable challenges. The fundamental problem with wormholes lies in keeping them stable and traversable. According to our current understanding of physics, any wormhole that forms naturally would collapse so quickly that not even light could pass through it. To keep a wormhole open long enough for matter to traverse it would require exotic matter with negative energy density, a substance that might not exist anywhere in the universe. The concept of exotic matter isn't just science fiction speculation. It emerges from serious theoretical physics. Quantum field theory predicts that empty space itself seethes with virtual particles that constantly appear and disappear. Under special circumstances, these quantum fluctuations can create regions of negative energy density, at least on microscopic scales. However, scaling this effect up to macroscopic wormholes would require manipulation of spacetime geometry far beyond our current technological capabilities. Recent advances in quantum physics have revealed intriguing connections between wormholes and quantum entanglement, the mysterious phenomenon where particles can be correlated in ways that seem to transcend the limitations of space and time. Some theoretical physicists propose that quantum entanglement might actually be a manifestation of microscopic wormholes connecting entangled particles through higher dimensions of space. This leads us into the realm of extra dimensions, one of the most speculative areas of modern physics. String theory, our most ambitious attempt to unify quantum mechanics with general relativity, suggests that space might have more than the 3 dimensions we experience directly. If extra dimensions exist, they could harbor entirely new categories of objects that would appear mysterious or impossible from our 3-dimensional perspective. Kaluza-Klein particles represent one such possibility. These hypothetical entities would exist partially in our familiar three-dimensional space and partially in compact extra dimensions. From our perspective, they might appear as ordinary particles with unusual properties, perhaps explaining some of the mysterious behavior attributed to dark matter. The Large Hadron Collider at CERN has searched for evidence of extra dimensions by looking for Kaluza-Klein particles in high-energy collision experiments. The concept of extra dimensions also opens possibilities for cosmic strings that exist in higher dimensional space. These objects would intersect our three-dimensional universe as point-like defects that could have properties unlike anything we've encountered. Detecting such objects would provide the first direct evidence for the extra dimensions predicted by string theory. But let's return to objects that, while extremely rare, are firmly grounded in observational astronomy. Orphan gamma-ray bursts represent one of the most puzzling categories of cosmic explosions. These events show all the hallmarks of long-duration gamma-ray bursts: the afterglows, the host galaxy environments, even the energy scales, but they lack the characteristic gamma-ray emission that defines the phenomenon. The discovery of orphan afterglows has forced astronomers to reconsider their understanding of gamma-ray burst mechanics. If these events can produce all the secondary effects of a gamma-ray burst without the primary emission, it suggests that the relativistic jets responsible for these explosions might be more complex and variable than previously thought. Perhaps we're seeing events where the jets barely form or point almost directly away from Earth. The Zwicky Transient Facility, operating since 2018, has been instrumental in identifying these orphan events by conducting rapid, wide-field surveys of the sky. By comparing images taken days apart, the survey can identify new sources of optical radiation that appear suddenly and fade over time scales characteristic of gamma-ray burst afterglows. This brings us to another category of cosmic rarities that challenge our understanding of stellar evolution: luminous blue variables. These are among the most massive and unstable stars in the universe, with masses exceeding 100 times that of our Sun. They undergo dramatic eruptions that can briefly make them among the brightest objects in their host galaxies, ejecting solar masses of material in spectacular stellar tantrums. Eta Carinae, located about 7,500 light-years away in the southern constellation Carina, represents the most famous example of a luminous blue variable. In the 1840s, this star underwent an eruption so violent that it briefly became the second brightest star in the night sky, as seen from Earth. The explosion ejected more than 10 solar masses of material, creating the spectacular homunculus nebula that we can observe today with modern telescopes. The rarity of luminous blue variables stems from their extreme instability and short lifespans. These stellar giants burn through their nuclear fuel so rapidly that they can exist for only a few million years, a cosmic eye blink compared to the 10-billion-year lifespan of stars like our Sun. Their massive size makes them prone to violent eruptions that can strip away significant portions of their outer layers. What makes Eta Carinae particularly fascinating is its binary nature. Recent observations using the Hubble Space Telescope and ground-based interferometers have revealed that Eta Carinae consists of two massive stars orbiting each other every 5.5 years. The violent eruption in the 1840s might have occurred when the two stars reached their closest approach, with one star's stellar wind colliding catastrophically with its companion's atmosphere. The fate of luminous blue variables remains one of stellar astronomy's great mysteries. Some might explode as hypernovae, supernovae with energies exceeding those of typical stellar explosions. Others might collapse directly into black holes without producing visible explosions at all. A few might undergo multiple eruption cycles before finally meeting their explosive ends. The study of these stellar monsters has implications far beyond stellar physics. Luminous blue variables in the early universe might have played crucial roles in enriching primordial gas clouds with heavy elements, enabling the formation of the first rocky planets. Their powerful stellar winds and eventual explosive deaths would have dispersed metals throughout their surroundings, seeding future generations of star formation. This cosmic recycling process connects us to another rare class of objects, population 3 stars. These hypothetical stellar giants would have been the very first stars to form in the universe, composed almost entirely of hydrogen and helium, because heavier elements hadn't yet been synthesized. If any population 3 stars still exist today, they would be among the rarest objects in the cosmos. Theoretical models suggest that population 3 stars were truly monstrous, potentially reaching masses of several hundred times that of our Sun. Without heavy elements to help them radiate away heat efficiently, these primordial giants would have been extremely hot and short-lived, burning through their nuclear fuel in just a few million years before exploding as parent stability supernovae, explosions so energetic that they would completely destroy the star, leaving no remnant behind. The search for population 3 stars represents one of the most challenging quests in modern astronomy. Because these stars would have lived fast and died young, any survivors would be incredibly ancient objects hiding among the billions of younger stars in our galaxy. Astronomers search for them by looking for stars with extremely low abundances of elements heavier than lithium, but distinguishing true population 3 survivors from merely metal-poor stars requires incredibly precise measurements. The pristine survey, conducted using telescopes in Hawaii and Chile, has been systematically searching for the most metal-poor stars in our galaxy. By analyzing the spectra of hundreds of thousands of stars, astronomers have identified candidates with metal abundances less than 1/10,000th that of our Sun. While none have yet proven to be true population 3 stars, each discovery brings us closer to understanding the universe's first stellar generation. The discovery of population 3 stellar remnants would revolutionize our understanding of cosmic chemical evolution, but they're not the only relics from the universe's infancy that might still be detectable today. Q stars, or quark stars in their most exotic form, represent theoretical objects where matter exists in a state that may have been common during the first microseconds after the Big Bang, when the entire universe was hot and dense enough to prevent quarks from binding into protons and neutrons. Unlike the strange quark stars we discussed earlier, Q stars would be composed of up, down, and strange quarks in approximately equal numbers, creating a form of matter that might be even more stable than atomic nuclei. If Q stars exist, they would be incredibly dense, even denser than neutron stars, yet potentially stable against gravitational collapse. A Q star with the mass of our Sun would be compressed into a sphere only 6 miles across. The formation mechanism for Q stars remains highly speculative, but some theories suggest they could form when neutron stars undergo phase transitions under extreme conditions. The core of a neutron star might suddenly convert to quark matter, releasing enormous amounts of energy, and potentially explaining some of the most powerful explosions observed in the universe. The transition would happen in milliseconds, transforming the star's entire interior structure. Recent advances in lattice quantum chromodynamics, computer simulations of quark interactions, have provided new insights into the conditions under which Q stars might be stable. These calculations require some of the world's most powerful supercomputers, simulating the behavior of matter under conditions that existed nowhere in the universe after the first few microseconds following the Big Bang. The Neutron Star Interior Composition Explorer mission has been measuring the masses and radii of neutron stars with unprecedented precision, searching for evidence of exotic matter phases in their cores. If some neutron stars contain significant amounts of quark matter, they would be slightly smaller and denser than predicted by conventional models, providing indirect evidence for these exotic states. But perhaps even more mysterious than exotic matter states are objects that might exist in parallel to our own universe. Mirror matter represents a fascinating theoretical possibility, an entire shadow cosmos of particles that interact gravitationally with normal matter, but remain otherwise invisible. If mirror matter exists, it could form mirror stars, mirror planets, and even mirror galaxies that occupy the same space as our familiar universe while remaining completely undetectable to conventional astronomy. The concept of mirror matter emerges from attempts to solve the strong CP problem in particle physics, a fundamental puzzle about why the laws of nature appear to treat matter and antimatter differently. Some theoretical solutions require the existence of mirror particles that are exact copies of ordinary particles, but interact through a separate set of forces. These mirror particles would be completely invisible to us except through their gravitational effects. If mirror matter comprises part of the universe's mysterious dark matter, then massive concentrations of mirror matter could gravitationally influence the formation and evolution of cosmic structures. Mirror stars might exist within our own solar system, their gravitational effects potentially explaining some of the anomalous motions observed in spacecraft trajectories. The European Space Agency's Gaia mission continues to map stellar positions and motions with extraordinary precision, potentially revealing gravitational signatures of invisible matter concentrations. The search for mirror matter exemplifies how the rarest objects in the universe might be hiding in plain sight, detectable only through the most subtle effects on their surroundings. This principle applies to many of the exotic objects we've explored. Their rarity often stems not from their actual scarcity, but from the extreme difficulty of detecting them with current technology. Moving from hypothetical parallel universes to confirmed astronomical phenomena, let's explore one of the most recent additions to the cosmic bestiary, collapsars. These represent a specific subclass of gamma-ray burst sources where rapidly rotating black holes form from the collapse of extremely massive stars. The term collapsar combines collapse and star, describing the catastrophic end of stellar giants that exceed 40 to 50 solar masses. The collapsar model, developed in the late 1990s, solved one of the major puzzles surrounding long-duration gamma-ray bursts. How could stellar explosions produce such tightly collimated jets of radiation? The answer lies in the formation of a rapidly spinning black hole surrounded by an accretion disk of infalling stellar material. The intense magnetic fields and rotation create conditions that can launch relativistic jets perpendicular to the disk plane. What makes collapsars particularly rare isn't just the extreme initial mass required, but the precise conditions needed throughout the star's evolution. The progenitor star must retain rapid rotation until the moment of collapse, which means it cannot lose too much angular momentum through stellar winds or binary interactions. Additionally, the star's core must collapse in just the right way to form a black hole rather than a neutron star. The Swift Gamma-ray Burst mission, launched in 2004, has detected and localized hundreds of gamma-ray bursts, allowing astronomers to study their host galaxies and identify the stellar populations that produce collapsars. These observations reveal that collapsar progenitors tend to form in galaxies with low metallicity, environments where massive stars can retain their rapid rotation more easily. The study of collapsars has provided crucial insights into stellar evolution in the early universe, when most galaxies had lower metallicity than today's stellar nurseries. Some astronomers speculate that collapsars might have been much more common in the distant past, potentially playing important roles in reionizing the universe and regulating early star formation through their powerful energy output. But even collapsars pale in comparison to the theoretical ultimate in stellar violence: hypernova explosions driven by magnetorotational instabilities. These hypothetical events would involve stellar cores rotating so rapidly that centrifugal forces nearly overcome gravity, creating conditions where magnetic field lines become twisted into configurations of unimaginable complexity and energy density. The energy release from a magnetorotational hypernova could exceed that of ordinary supernovae by factors of 10 to 100, making them visible across cosmological distances even with modest telescopes. If such events occur, they might explain some of the most luminous transients detected by surveys like the Catalina Real-Time Transient Survey and the All-Sky Automated Survey for Supernovae. The rarity of these extreme explosions would stem from the extraordinary fine-tuning required in the progenitor star's properties. The stellar core must be rotating at nearly the breakup velocity while maintaining the precise magnetic field geometry needed to store and suddenly release enormous amounts of energy. Computer simulations suggest that such conditions might occur in fewer than 1 in 10,000 core collapse events. These investigations into cosmic explosions bring us to consider objects that exist at the very boundaries of detectability: gravitational molecules. These theoretical structures would consist of two or more black holes bound together by their mutual gravitational attraction, orbiting each other in complex, quasi-stable configurations that could persist for millions or billions of years. The formation of gravitational molecules would require incredibly precise initial conditions, black holes with just the right masses, positions, and velocities to become gravitationally bound without immediately merging. Once formed, these systems would slowly spiral inward as they lose energy to gravitational wave radiation, but the in-spiral timescales could be extraordinarily long for certain orbital configurations. The detection of gravitational molecules would require next-generation gravitational wave observatories capable of monitoring the sky continuously for years or decades. Unlike the brief chirps produced by merging black holes, gravitational molecules would produce persistent, slowly evolving signals that might be detectable months or years before the final merger event. The Laser Interferometer Space Antenna mission will have the sensitivity to detect gravitational molecules throughout the observable universe, potentially revealing a hidden population of complex gravitational systems. If such objects exist in significant numbers, they could provide new insights into the formation and evolution of the first black holes in the universe's history. As our journey through the universe's rarest objects approaches its end, we arrive at perhaps the most philosophically profound category: cosmic domain walls. These hypothetical structures would be two-dimensional surfaces stretching across space, marking boundaries between regions where the laws of physics themselves might be subtly different. Imagine sheets of altered reality, thinner than atomic nuclei but potentially spanning billions of light years, separating domains where fundamental constants have different values. Domain walls would have formed during phase transitions in the very early universe, similar to how ice crystals form boundaries when water freezes. As the cosmos cooled from its initial state of perfect symmetry, different regions might have settled into slightly different vacuum states, creating walls where these regions meet. The energy stored in these boundaries would be enormous. A domain wall with the thickness of a proton, but stretching across our galaxy, would contain more energy than all the stars we can observe. The search for domain walls represents one of the most challenging endeavors in cosmology because their effects would be incredibly subtle. A domain wall passing through our solar system might cause minute changes in the values of fundamental constants, potentially detectable only through the most precise atomic clock measurements. The Global Positioning System, originally designed for navigation, has inadvertently become one of our most sensitive tools for searching for such exotic phenomena. Recent advances in atomic interferometry and optical clock technology have reached precisions that allow scientists to test whether fundamental constants truly remain constant across space and time. If domain walls exist and occasionally pass through our local region of space, they might cause tiny but measurable fluctuations in the fine structure constant or the electron-to-proton mass ratio. But even domain walls seem mundane compared to our final category of cosmic rarities, stable strange matter nuggets or strangelets that might have survived since the universe's Quark epoch. If strange matter truly represents the most stable form of matter, then primordial strangelets formed in the first microseconds after the Big Bang could still be wandering through space today, representing the oldest structures in existence. These ancient wanderers would be older than galaxies, older than the first stars, older than any structure we've ever observed. A strangelet that formed when the universe was 1 microsecond old would now be traveling through intergalactic space, having witnessed the entire history of cosmic evolution. It would have seen the formation of the first atoms, the birth of the first stars, and the assembly of the cosmic web that connects all galaxies. The detection of a primordial strangelet would revolutionize our understanding of the universe's earliest moments and provide direct evidence for the quark-gluon plasma state that dominated the cosmos before normal atomic matter could exist. However, these objects would be incredibly difficult to distinguish from ordinary asteroids or comets unless we could somehow sample their internal composition. The Alpha Magnetic Spectrometer aboard the International Space Station has been searching for strange matter signatures in cosmic rays since 2011. By analyzing the properties of particles arriving from deep space, this experiment hopes to identify the unique signatures that would indicate the presence of strange quarks in cosmic ray nuclei. As we reach the end of our exploration, it's important to recognize that the rarest objects in the universe serve as more than just cosmic curiosities. They are laboratories where nature conducts experiments we could never perform on Earth. Each discovery forces us to expand our understanding of what's possible, challenging our assumptions about reality itself. The search for these exotic objects also represents humanity at its best, our insatiable curiosity driving us to ask questions about phenomena so rare and distant that they have no direct impact on our daily lives. Yet through studying them, we learn fundamental truths about the universe that ultimately help us understand our own existence and place in the cosmic story. Consider the remarkable fact that the calcium in your bones was forged in stellar cores, the gold in your electronics was created in Kilonovae explosions, and the iron in your blood was scattered by ancient supernovae. We are quite literally made from the ashes of some of the universe's most violent and rare events. Every atom in your body has a cosmic biography spanning billions of years and involving processes of unimaginable extremity. The James Webb Space Telescope, the Vera Rubin Observatory, and the upcoming Extremely Large Telescope will undoubtedly discover objects so rare and exotic that we haven't yet imagined them. Each new generation of instruments reveals phenomena that challenge our theoretical understanding and force us to revise our models of how the universe works. Perhaps most remarkably, some of the rarest objects we've discussed might not be rare at all on cosmic scales. Dark matter stars, Axion clumps, and primordial black holes might exist in vast numbers throughout the universe, remaining invisible only because they interact so weakly with ordinary matter. We might be swimming in an ocean of exotic phenomena without realizing it. The possibility that we're surrounded by invisible rare objects speaks to one of the most humbling aspects of modern astronomy. We can directly observe only about 5% of the universe's total content. The remaining 95% consists of dark matter and dark energy, substances whose nature remains completely mysterious despite decades of intensive research. This cosmic humility should inspire rather than discourage us. We live during an extraordinary period in human history when our technology has finally become sophisticated enough to detect gravitational waves, image black holes directly, and search for planets around other stars. Each of these capabilities was pure science fiction just decades ago. The young people watching this video today might become the astronomers who finally detect primordial gravitational waves, discover the first confirmed dark matter star, or identify signatures of extra dimensions in particle accelerator experiments. The universe's rarest objects are waiting to be found by curious minds willing to push the boundaries of what's possible. As you look up at the night sky tonight, remember that you're seeing only the tiniest fraction of what exists out there. Between the visible stars lie cosmic voids populated by wandering rogue planets, streams of dark matter flowing through space like invisible rivers, and perhaps exotic objects so strange that we haven't yet developed the concepts to describe them properly. We began this journey by comparing rare cosmic objects to finding needles in haystacks the size of galaxies. But perhaps a better analogy is that we're explorers who have just learned to build ships, setting out to map an ocean whose shores we can barely imagine. Each discovery reveals new continents of possibility, new questions to investigate, and new wonders to inspire future generations of cosmic explorers. The universe's rarest objects remind us that reality is far stranger and more wonderful than our everyday experience suggests. In a cosmos filled with such magnificent mysteries, how can we do anything but look up in wonder and keep searching for answers to questions we haven't yet learned to ask? The greatest discoveries in astronomy often begin with someone noticing something that doesn't quite fit, something that seems too rare or unusual to be real. Your curiosity about these cosmic mysteries connects you to every human who has ever wondered about the stars, from ancient astronomers tracking planetary motions to modern scientists detecting gravitational waves. We are all part of the same quest to understand our place in this magnificent, mysterious universe. The rarest objects we've explored today are also the most precious, not because of their scarcity, but because they reveal truths about existence itself that we are only beginning to comprehend.